Okay, hey folks, let's continue on. Let's build up the p orbitals. To do that, you can see we're going to have to use a basis set, and we're also going to get this interesting function in R, which shows us the directionality of our p orbitals. And you can see I've also got a little Mathematica thing going on here for visualization purposes. Okay, so building up the p orbital, and we're going to take it one p orbital at a time. So we'll start with z. So we will define a pz orbital as psi star psi, right? Where my psi is given as 2, 1, 0, which means we need r21 and y10. And as we build this up, we will see that this actually equals z times some function in R, where that z comes from our coordinate transformation, z equals r cosine theta. So going from the spherical coordinate back to the Cartesian coordinate. Okay, so putting all of this together, let's do it. So we can say psi pz, or I could have wrote that as psi 210, equals the following. I'm going to have all of those constants. So that's going to be 1 over the root 24. And then now that's times charge z over Bohr radius to the 3/2 power times this function in rho, which now recall rho for 2p is going to be 2zr over 2, right? Because n is now equal to 2 times my Bohr radius. So that just becomes zr over a. Excuse me. So let's write that down, zr over a. And now that's going to be e raised to the negative zr over 2a power. And then we've got to multiply that by the angular component, which is root 3/4 pi times cosine of theta. Okay, so now adjusting this algebraically and using a little bit of foresight, I'm going to combine the r and the cosine of theta, right? Because we noted up here that that seems like a practical thing to do. We can combine all of these constants, like 1 over the square root of 24 and root 3 over 4 pi, into the following. And I did that already. I don't expect you to just be able to call this up on the top of your head, but we could simplify all those constants to 1 over 4 times root 2 pi. And then we can combine the z over a with the z over a to the 3/2 power, and that becomes z over a to the 5/2 power. And then we end up with an e to the negative zr over 2a. And now what we will see, if we continue to go down the rabbit hole, my r times cosine theta, if I make that Cartesian coordinate transformation, just equals z. And all of this stuff we will call f of r. It's just some function in r. So let's take a look at what this looks like. So you can see there's a picture of it right there. But here now in my Mathematica, I've got all of this stuff in, and I punched it in exactly like was given from these tables. You know, there's the 1 over root 24. I made z equal to 1 for hydrogen. Here's my y10. And to make this easier to view, we're just going to look at it at the expectation value of the radius. So giving it a constant radius of 264.5. And now when I take psi squared, right, because remember the orbital is psi star psi, and here I just squared it because there's no imaginary numbers, lo and behold, we get this beautiful p orbital shape. Another thing that I want to note here is, remember, we're looking at psi squared, which means the values are positive. Colloquially, we use a positive and negative sign here to indicate different phases of the wave function, those phases being its different direction dependencies. So when this graph is, or when the graph of this thing is put on this Cartesian space, we can see there are regions in the positive areas and regions in the negative areas. So this is somewhat arbitrary to call this positive negative, but it's a better indication of the phase of the particular lobe in the orbital. So let's keep going with this, and let's try to put together px and py. So we can take a page out of the solution for pz, which was z times f of r, and note that because all of these are degenerate ml values, right, from L is equal to 1. So we will see that these are all from the degenerate. ML is -1, 0, and +1. Then Px should be x times the same function in f of r, and Py should be y times the same function in r. So all of these f of r functions should be the same. Recall, however, when we looked at more than one dimension, we got uncertainty in the other dimension. And we noted that we put all of our lot into the z dimension, which gave us this nice shape. So to describe the x and y dimensions, we're going to need a superposition. And so here is how we're going to build that up. So we can define the ml plus 1 state as the following: psi2 1 plus 1, right? Remember, that's the ml value, as the p plus wave function. So all of this we'll just simply note is the p plus wave function. We'll call the ml -1 value the p negative wave function. And thus our basis set will be some normalization constant times a linear combination of the two. And because it's plus or minus, we need both. So specifically, px becomes 1 over root 2 of p plus minus p minus. It's 1 over root 2 because, remember, my orbital is going to be squared. So that becomes 50-50. It's 50% p plus, 50% p minus. And now, due to the appearance of imaginary numbers, my py becomes I over root 2 in the normalization constant times p plus plus p minus. So there's our plus or minus possibilities. And we shouldn't be worried about this I, right? Because when we square it, it becomes -1. But as we'll see, that I is important the way it gets distributed through. So now, building this up, we have our two basis sets. We'll note that the px orbital is defined as px star px, and the py orbital is defined as py star py, because hopefully we recall those ml -1 and ml +1 solutions contain imaginary numbers. So we need to take the proper square modulus. And so if we were to go through and work through that algebra, which I'm not going to do on this slide, we would arrive at the following. We would arrive that the linear combination of p plus minus p minus works out to be r sine theta cosine phi times that exact same function in r that we developed for pz. And from our Cartesian to spherical coordinate transformation, r sine theta cosine phi equals x, which is pretty cool. And similarly, our py, we would find that we get r sine theta sine phi, and in our coordinate transformation, that equals y. So this can be done with some real pain in the butt algebra to show that this f of our function is the same for all three orbitals. So now let's take a look at what those look like. So here in my Mathematica, you can see I'm defining the ml -1 and ml +1, and you can see that they do contain imaginary numbers, which is why we need to do the proper square modulus. And then here is my psi px, right, which was 1 over root 2 times the, so I wrote this as P negative minus P positive, but that will be the same as P positive, or no, excuse me, I think I did that correctly. Okay. It's fine, we'll just keep going on. We'll assume that I either made a mistake or I didn't, and it's probably inconsequential. So now when we look at the square modulus, which remember has to go conjugate psi px times psi px, we get the following shape. It looks strikingly similar to what we got for pz, albeit in a different orientation. And we also see the same thing about the respective phases. We can see regions of the wave function out into the positive areas, and we can see regions of the wave functions out into the negative regions. And again, remember, those are phases, not necessarily signs of the wave function. And then now we can do the same basis set for py, I over root 2 times p plus p minus. And now what we get is another one of these shapes with the appearance of different phases. And the way that we know we did this correctly, if we put them all together on the same plot, you can see that they now all have recovered their directional dependence in the z, x, y, which is pretty cool. And so that's why we can see that that f of r function has to be the same, because they are all degenerate. They just all have different directions given by the Cartesian dependence x, y, and z. Awesome stuff. We'll do the same thing for d orbitals in the next video.